Hello world, it's Craig. There seems to be an increasing interest in the STD bus. At least there's a fairly active and growing STD Facebook group, and lately much of the reasonably priced STD hardware on eBay has been getting snatched up fairly quickly. But since price and availability of good STD bus processor boards can be hit or miss on eBay, I'm creating a few STD bus boards. I'll put the build files on the sbc85.com project site so you can order them yourself from a PCB house. I'll also be placing a PCB order later this month, so I'll have a few boards on Tindy if you need them. The first board is a simple pad-per-hole prototyping board. And this board includes labeled headers for the STD bus signals, has clearly marked rails with 5 volts and ground. The 5-volt pads are square, ground pads are oval, and unconnected pads are round. And this should just be a useful prototyping board for anybody that's interested in dinking around with STD. Once I get the next batch of boards sent off to the house, I'll be putting the design files and the documentation up on the sbc85.com website, but right now I'm busy getting these boards finished up. So I'll get to putting the files up on the website later. The second board that I'm working on is an 8085 single board computer. I'm just finishing up the design, and it's going to be the subject of this video, and I'll finish up talking about this board in the next video also. If you want to copy the schematic, there's a link in the description. And I thought it'd be worthwhile to share the design and see if there's any suggestions or if somebody can help find any mistakes in it before I submit the boards for fabrication. I think one of the better descriptions for the STD bus is in the WinSystems catalog. There's the specifications for STD. They have best practices. And then they've also have a section on the 16-bit transfers, which was one of the first extensions of the STD bus. So this is a good source, and I think this is available on BitSavers, the digital version of most of this. I suppose if not, I could scan those few pages. There's also, I know these are available on BitSavers, there's also the Prologue STD Bus Technical Manual and Product Catalog. This also lists products. And then there's the 1981 Technical Manual and Product Catalog. So these are also very good references, and they give you good information on what's needed to design with STD. I wanted to give a little bit of an incentive for people to invest some time in this board, so I'm going to award a prize to the first person that can find a design mistake that would prevent this board from operating as intended. I need to defend my herd of STD boards, so I'll send one of my spare STD boards to the first digital design guru who finds a mistake in this. We can decide on the details later, what board and so forth after somebody finds the mistake. It'll most likely be a Prologue, either a CPU or a Prologue I/O board of some type. So you can put your thinking caps on. I don't know how many designs are left in this mistake. I just found another one yesterday, but I'm only giving one board away. So first come, first serve. If you think you have found a mistake, please get the latest version of the schematic and make sure it hasn't already been discovered and corrected. So as I said, I'm going to do this in 2 videos. The first one, I'm going to cover the general features of the board and focus on the core components. And the core components are the 8085 microprocessor, the 8155 RAM and programmable I/O, the serial interface, a little onboard output port, onboard memory, and the system address decoding. All of these around the outside are STD drivers and things required for the STD bus. In the second video, we'll come back and we'll look at all of these and exactly how we drive things and put things onto the STD bus. So I'm going to save STD for the second video. Right now, we're just going to look at the core of this board and the features of that. The 8085, 8155 design part of it is quite conventional with the address decoding aside. So the address decoding is probably the most complicated part of this board, but the 8085, 8155 is very straightforward, just textbook type of connections between those. I don't think there's any mistakes in that. So the 8155, if you're not familiar with it, it has 256 bytes of RAM and it has 22 bits of programmable I/O. So this is configured as 2 8-bit ports and a 6-bit port. The intention of the 6-bit port is either as I/O or it can do handshaking for the 8-bit ports. The 8155 also has a 14-bit counter that can be used as a timer. And on this board, the tick input for the counter is normally driven by the processor clock, but it's jumper selectable, so the user can take that jumper off and patch that tick input to whatever source they might want to have, either on board or something they bring in from the ribbon cable. Likewise, typically the timer output is connected to a numbered reset on the 8085, and typically that would be the restart 7.5. But again, the user can reconfigure that if desired. It comes out on a header. Let's see, the header's over here. That comes out over here on this header. So if the user wants to, they can reconfigure the tick output also. So finally, on the 8155, the I/O, you can see that the I/O comes off onto this header, and the header is just mounted up against the top of the board. It's just you can use an IDC ribbon cable to go off to a little proto board or something. There's an additional little patch that also ties into this header. So there's 8 pins here that are designed that you can go around the board, take some signals you want, either bring signals off or on the board, and those also connect into this 34-pin header that goes off board. So that just gives you the freedom to add some signals that you want to this off-board header. Okay, so next up is the serial port. Just using the 8085 SID and SOD lines, they run through this MAX 232 for inversion and level shifting to the plus and minus 12 required for true RS-232 signals. The hardware handshaking isn't pre-wired, but the extra drivers come out to a little header here so the user can utilize any of those extra drivers that they want. Now the port, this doesn't have a UART, so the port is just going to be a bit banged out, the SID and SOD lines. Probably the most unique aspect of this board is the onboard memory configuration. And that's what we're going to spend pretty much the rest of this video talking about, is the memory and how that memory is decoded. Of course, with STD Bus, there can be various forms of memory on other boards, and some of those other boards may be fairly rigid in their configuration. They might be quite flexible. It can be fixed memory, it can be paged memory, but this board, in order to operate with some of the old vintage STD cards available, it needs to be flexible enough to contort its memory mapping around some of the other boards in the system. So for onboard memory, we have 3 28-pin universal memory sockets. So the universal socket allows the user to populate each socket with RAM or ROM as needed. So any of the memory devices up to 28-pin can be used. 2 of them are standard sockets, and the third one is a ZIF socket for easy exchange of programs you might be writing. And finally, before I forget, there is a little single 8-bit output port. By default, 6 bits are connected to LEDs, and these LEDs are near the top of the board. You can just play with those LEDs. 1 output is used to directly toggle a speaker, and 1 output is used to configure the memory map, which we'll get to next. So let's finish up this memory discussion. Since memory devices can be of various sizes, it presents a bit of difficulty in decoding the addresses. If you go back and you look at the SBC85 project board that I did a year or 2 ago, it has some fairly stringent requirements on what you can put in the sockets. And so configuration is pretty much foolproof. You just set a couple of jumpers and you're good to go. But on this one, there's a couple of things I wanted to add to give us much more flexibility in the memory mapping. So the decoding technique needs to be flexible enough to satisfy any possible configuration of the memory devices on this board, as well as what you might have in the remaining part of the system. But I still wanted to avoid using any custom program chips like PALs or GALs, and obviously the decoding needs to consume the minimum amount of real estate because even an STD card is not that large. Then to further complicate matters, ideally this board should be CP/M compatible. Now remember that the 8085 fetches its first instruction at 0 hex. But to run CP/M, the hardware needs to be able to start boot code at 0. So somehow it has to get from that 0 hex into the boot code. But during initialization, the hardware needs to remap memory so that now RAM starts at 0. So CP/M, when it's operating, requires that the RAM is at 0. Then the ROM, with device drivers and such, is at the very top of the 64K memory space. So that creates a bit of a conflict. You have to boot at 0, but as soon as you boot, you have to replace 0 with RAM. And there's various ways of doing that, of swapping memory maps, or inverting a address bit, or just disabling the ROM and enabling a RAM at the same location. So there's various ways, that have been done over the years to deal with that with CP/M. But on this board, making the memory decoding adaptable enough to handle any kind of chip in these universal sockets and to be able to run CP/M required it to either be able to swap a couple of these sockets around, the RAM and the ROM, or fold back memory, or otherwise fiddle with whatever chip selection there is to meet the CP/M required memory configuration, allow the user to configure this part however they want, and still be able to work around what other memory boards are in the system. So key to this is the address decoder, and all of this you see here is the address decoder. So let's go over that. The method I used for decoding the address, it's a fairly old method, and it works like this. The 3 high address bits feed this 1 of 8 decoder, and so this breaks the 64K memory space down into 8 8K blocks. So A15, 14, and 13 feed this 74, 156, 1 of 8 decoder. Depending on those 3 address lines, one of these outputs will be low at any time. The enable inputs are tied active, so the outputs are always going to be enabled. So one of these is always going to be low. Now, whenever an address is put onto the bus, if the address starts with 000, then pin 9 goes low, 001, pin 10, and so forth, all the way up to the address beginning with 111, which is the highest output, and pin 4 goes low, and all the others are going to be high. Since this is not gated yet with any other signal that indicates we have a valid address, we'll get some rippling through that. So we need to make sure that later on when we actually use that decoding, we've waited until it's actually known to be a valid value. We need that to prevent inadvertent enables as the address bit settle into their final value. All right, so we have these 8 lines that indicate which 8K block is being addressed. Now, each device has a switch to select which of these outputs are used to enable that memory device. So here are the 8K address blocks associated with each of the decoder outputs. And each of those are connected to the switches. These switches have a common rail that terminates here on pin 9. So the output of the switch follows the decoded lines of the closed switches. So this is the device for the memory 1 socket. Anytime you want that memory 1 socket to be enabled, you just close that switch for that address block. When that line goes low, pin 9 is going to go low, and then that is used to enable that memory socket. The 74156 is open collector, so they're essentially in a wired AND configuration. If more than one switch is closed in the package, it just maps that particular socket to multiple 8K memory blocks. Now there's a couple of downsides to this technique. The first is that, and it's a very minor issue, in that the memory blocks are 8K in size. So if a memory device used is less than 8K, so you want to use a 2732, for example, then the rest of that 8K block is wasted. It's mapped to that device, and even if you're using a device smaller than 8K, it's mapped to that and nobody else can use it. Now there's no maximum memory size. If all the switches are closed for a particular device, then the memory is mapped up to the maximum of 32K memory space. Now you could do a little wire wrapping between some jumpers on this and use one chip all the way up to 64K. I didn't include that as jumpers. I thought that was going to be an obscure enough configuration that it didn't need to be in jumpers. But you can use wire wrapping and going across the various pins here to get connect address 15 so that you can use one chip even for all 64K. Now, nice thing about this decoding technique is you can leave holes in the map. So for example, if you've got memory in your device and some other card that just is not very flexible, it's got a fixed or a very small range of memory choices that you can configure it, you can leave an 8K hole in a device selection, say just by closing the first, the third, and the fourth switches. That would leave the second one open. And then that device would be mapped to the first 8K. It would skip the next 8K, and then the third and fourth 8K blocks would be mapped to that device. Of course, the 8K that you're skipping is just being wasted in that particular device, but if you have something else in the system that has to use that memory address, it gives you the opportunity to put a hole and map around that memory location. So this type of memory decoding is flexible enough to handle a lot of situations. So that first limitation was that it'll waste memory if your devices are less than 8K, but that seems unlikely. Nowadays, nobody's going to be using anything smaller than a 2764 EEPROM and a 6264 RAM in these sockets. So the second drawback of this system is that with that flexibility comes the opportunity to misconfigure the map. And when I show you the model here for the board, I'll explain how I tried to reduce the opportunity for error, at least make errors easy to spot when you've set these switches. But it is easy to accidentally overlap devices into the same memory space. But at least the concept is straightforward. Using the most significant bit, each output of this decoder is 8K. The switches are used to select which of those 8K blocks enable the onboard memory for each of these devices. If the device is 16K, you just pick 2 blocks, close 2 consecutive switches, 4 switches for a 27256, and so forth. Now, for the 8155, rather than reserve an entire 8K block, one of these blocks is further broken down into 8 1K subblocks. And one of those 8K subblocks then is used to select the 8155. Another one of those 8K subblocks is used to select the onboard output port. So you've undoubtedly noticed that there's a lot more switches on this than there are devices. In fact, there's 2 SIP switches for each of these devices. These are for the memory 1 location, these 2 are for the memory 2, memory 3, and these are for the further subdivided 1K block that is down here. So these sets of switches on the left side is for the default memory map. The second set is for an alternate memory map, and the user can swap back and forth between those 2 memory maps by setting the least significant bit on this output port. So if the user wants to run CPM, for example, this alternate configuration will allow the RAM and the ROM to just be swapped, to be completely paged in or out, for example. So you may have one of these as being just the boot ROM, and then when you go to the alternate memory configuration, you just completely page out that boot ROM and swap in a operating system ROM. As an example, the first socket can have a EEPROM mapped at the bottom of the memory space in the default, and it can have a RAM mapped at the top of the memory space in the default. The ZIF could be mounted or could be mapped anywhere in between. And then in the alternate map, the RAM and the EEPROM are just swapped. And again, the ZIF can be in the same spot, it can be moved someplace else, or it could just be completely paged out. Likewise, the 8155 and the onboard port have a default and an alternate mapping. And so they can either be in the same space in all map configurations, or they could also be moved to a new space. As I mentioned earlier, it's the least significant bit of that output port that's the bit that swaps between the 2 mappings. You set the bit to use the alternate map, and it follows this set of switches. You clear the bit for the default map, and it follows this set of switches. On power up reset, this is cleared, and so power up, we're using the default mapping. Now there's 2 of the LEDs that are on the top edge of the board that tell us which map we're using. To switch between the default and the alternate map, this least significant bit controls the 74157 multiplexer, which simply selects between the 2 mappings. So all the pin 9s of all these switches comes down to this 74157, and that then depending on this swap bit on pin 1, that determines whether it uses the default switches as output or if the alternate switch settings are output. So once selected by the memory decoder and this multiplexer, the select signal is gated with the IOM to limit chip select to memory operations. The 8155, of course, internally decodes the IOM, and the onboard port uses both the IOM and the write strobe to determine when it needs to clock in and latch the data on the address data bus. If it hadn't been for the 8155, which responds to both port access and memory access, I could have eliminated all 4 of these 7432 in this quad 2-input OR by using the enable on this multiplexer and just connected that to the IOM, but I needed to be able to have this multiplexer on for both memory and IO writing for this port and the 8155. So tried as much. I could not get rid of this 7432 by using that enable. Maybe somebody can come up with a good idea on how to utilize that enable rather than all of these OR gates. Here's a rendering of the board in its current design, and as you can see, it's fairly tightly packed. At the bottom are the transceivers to satisfy the STD bus requirements, and that's what we'll get to in the next video, are those transceivers. There's a 5-volt input barrel connector for when you just want to operate the board by itself and not in a backplane. These two 40-pin dips are the 8085 and the 8155. The 3 memory sockets are here near the top, with the one on the right being a ZIF, so there's extra room here for the ZIF, and hopefully the handle of the ZIF socket clears this 90-degree header on the top. This is the header for the 8155 I/O, as well as those 8 extra. This is the little header that allows you to pick up different signals from pins around the board and wire wrap them up to this off-board connector. Then towards the left, we've got the serial port. We have the reset switch, and there's LEDs here to show us that we have power and which memory map is in use, and then the other 6 LEDs that you can just play with the outboard port. The configuration jumpers for the type of memory device used in each of the sockets are over here along the right edge, and those you don't have to wire wrap, you can just use shorting plugs for those. Back on the top left, there's some glue chips. The Max 232 is down here. You can see its capacitors. These are a little bit more glue chips. Here are the 10 address selection SIP switches for the decoder. And you don't have to use SIP switches if you don't want to. You can just put a header in and wire wrap that configuration if it's easier for you. It'll certainly be cheaper. Some of these SIP switches can be pricey. Now, back to the configuration error I mentioned as a problem with this. The switches are grouped so that the 4 default map SIPs are adjacent here on the left, and the 4 alternate map SIP switches are also adjacent here in the center, and the 2 on the right are for the 8155 and the onboard port. So at a glance, you can confirm that at most 1 switch is closed for each 8K memory block. So you just go across the rows of these 4 and make sure that any switch position is only closed in 1 row. You can have multiple switches closed for any device to claim multiple 8K blocks, but any 8K block should only be used once and only enabled for 1 device. Then likewise for the alternate map, you do the same. Go across these rows, make sure that any address block is only used once. And the reason that's a problem, of course, is that if multiple devices are assigned the same memory block and both are enabled, on any line where the data bits are different, they will be in contention, and so something's going to start getting hot. So we want to avoid contention on these memory devices. But I think that the way that those are arranged, it's going to be pretty easy to make sure that you don't have a misconfiguration in the memory. I did consider including protection to prevent enabling more than 1 device at a time, making them mutually exclusive, but it would have taken another couple of logic chips, and it just hardly seemed worth the effort. I don't think it's going to be that big of a problem. You can think these things through. Then finally, somebody had asked for a sandbox to be on this. So there's a little pad per hole area. I think this is 17 by 18. I forget exactly the size. There's power and ground brought to the edges. So the square pads down here are 5 volt and the oval pads up here at the top are ground. So there's quite a bit of power and ground. There's a nice pad per hole area. And then finally, there's a speaker. I mentioned the speaker was the most significant bit of the output port. But if you would rather have the sandbox than the speaker, you can just leave that speaker off. The pad per hole array continues underneath that speaker. Alrighty, this is the design for the core elements. The layout's pretty near done unless somebody finds a mistake. Next time we'll go over the STD bus requirements, the signals, and these elements around the edge, which are there for the STD interface. So, let me know if you're interested in this project. We'll do the next video for sure, but then we'll see if we'll do any videos after that on this board. As always, the content on this channel is fueled by thumbs up, likes, user engagement, sharing, and so forth, and of course subscribers. All right, thanks for watching. Talk to you later. Bye-bye.